Okay, so got to do something about the view. The view isn't right by me. Let's see. There we go. That's it. That's the view I like. Okay. All right. So I'm going to turn my computer around. I'll get to you in a sec. Hold on. All right. Okay. Well, today I think we learn about some pretty important stuff that have to do with reaction rates. So, it's like the 4 classes, the 4 lectures on kinetics are like almost 4 completely different topics. I mean, the first day we did kinetics, we were looking at, how concentration, how the rate law depends on concentration. So we did that. So we did rate laws depend on concentration. So that was day 1. And then last time we did for first order reactions, we looked at how concentration depends on time. So that's kind of like a very different topic. And today we're going to do something that's called collision theory, which has to do with the things that have to happen for a reaction to actually occur and how they affect the rate of that reaction. So that's collision theory. And then next class, which will be the last class on rates, will be on what we call mechanisms. So those are sort of the steps in a reaction. So that's what we'll be doing next time. But this collision theory, this is where you'll learn why reaction rates depend on temperature. And this is what we're going to do in lab next week. Okay, so hopefully I'll get to, the last thing that I have to tell you before you will have what you need to actually do that lab next week. All right, so last time, I just said it really. Last time I told you about first order reactions and how concentration depends on time. So this is really a major shift in gears from last class because we're not doing that at all anymore. So it's almost like 4 separate topics. So today I'm going to focus on second order reactions. So it's mostly I'd like to focus on second order reactions because these are reactions. It's called collision theory. So what I'm telling you now has to do with when there's a collision in a reaction. And so you really can't have a first order reaction that wouldn't have a collision. It's basically one thing doing something. So, if we have a reaction that's second order, and one possibility would be the reaction that's just A and B going to products. And let's say it's second order and that the rate depends on both of these reactant concentrations, each to the power 1. And now this rate constant, this is really what we focus on today. Collision theory will give you information that you can use to know, what the value of that rate constant depends on, how does it change with temperature, things like that. So we're really focusing on this rate constant and what it depends on. And the reason why we spend so long on this, well, one full big class, the reason why that's important is because these rate constants have a huge variation in their values. I mean, they can be 10 to the minus 9th to 10 to the 9th, even 10 to the 10th on it, which is right. I mean, look at that. That's 18 factors of 10 in variation in what this K can be. So the question is, why is there this enormous, absolutely enormous variation in the values of the rate constant? And that's kind of what we're looking at today. Okay, and like I said, it has to do with what has to happen in a reaction. So we'll just write that down. What has to happen in a reaction, in particular, one involving a collision between two molecules, because you can have a reaction where one molecule just sits there and decomposes into something else, breaks down. All right, but what I'm talking about, what has to happen in a reaction involving a collision between two molecules, okay, or two atoms. So obviously, what do you think has to happen? If two molecules have to collide in order to react, then the first thing that has to happen is that a collision must occur. Well, collisions occur all the time. Okay, molecules, when you have, 1 mole or half a mole of different molecules in a solution, they collide a lot. Okay, so collisions occur at a very, I guess I would say this happens. And I'm really talking about in solution, at very high frequencies. In the gas phase, it would be not as high, right? Because the molecules are just concentrated in the gas phase. They're way, they're not separated from each other. But even in the gas phase, there is a reasonably high number of collisions. But anyway, so that's the first thing that has to happen. Obviously, if a reaction relies on a collision, then the collision has to happen. And usually that's a pretty high frequency. So we call it the frequency of collisions. I'll come back to that. But there's another important thing that has to happen during that collision, and that is that it can't be necessarily just any collision. There must be the proper orientation of the molecules involved. And I'm going to show you an example very shortly, so you can hold off on that one, because I want to give you the third thing that has to happen. So I would say that I would give a but to this, but even if two molecules collide and have the proper orientation, they still might not react. They still need to have something else. They still need this number 3. It's called the activation energy. And this is it's like a bump. There's a little energy bump, not necessarily little. The activation energy is the bump, the energy bump in the path from reactants to products. Okay, and so that's one of the very important things that we talk about today is activation energy. So I'm going to get to activation energy a little bit later. So what I want to talk about first are the first two. So these are just the 3 things that I just wrote down, so you don't have to write them down again. The reactions collide, we call that a collision complex. So, you get A plus B, it forms this A ... B. That's what we call a collision complex, okay, where they're together, right? And that has to be oriented properly, which I'm going to show you in a minute. And then it also has to have that enough energy to form products, to go over that little, or not necessarily so little, energy bump. Okay, so here I want to show you an example. And I'm talking about orientation here. So what do I mean by a proper orientation? Okay, so here's a reaction. Oh, geez. Looks like I didn't. Oh, here it is. ClNO2. Let me write that. ClNO2. This is in the gas phase. Plus NO goes to NO2 plus ClNO. Okay, so let's take a look at these molecules. All right. ClNO2. Okay, here is the NO2 part of that molecule. And here's the Cl. These guys are all bonded together. All right. A little bigger. So this is the ClNO2 here. And then we just have NO. All right. And so what's going to happen, and you could see that now you have a bond between the N and the Cl. These are the products. So a bond is going to form between this N and this Cl. Okay, so clearly this N has to point at the Cl. All right, if it's not directly pointing at the Cl, then the products aren't going to form. Okay, so these have to point at each other. To form a bond. Okay, so what I'm going to show you is a couple of incorrect orientations. All right, so let's go down here. And this is showing, okay, so what if instead of the N pointing at the O, the N is on the other side and the oxygen is, sorry, instead of the N pointing at the Cl, the oxygen points at the Cl. Well, there's no way that's going to result in the product that I showed you, okay? You can't form a bond from N to Cl if the N is not pointing at the Cl. Okay, so here, if NO is flipped and the O points to the Cl of the ClNO2, then no reaction. That's the wrong orientation. And here, I have the N now in that direction, but it's coming at the oxygen instead of the Cl. Okay, so here, N of the NO points at O of ClNO2, and that's the wrong orientation. And so there will be no reaction there either. So both of these are incorrect orientations. So, you know, how do we account for this? How do we, how does that affect the rate constant? Because these things affect the rate constant. So I'm going to give you an equation. I mean, I know that people don't like math, but some of you do, right? But in any case, this is a very important equation. And what it does is it puts everything in here. It's got the collision frequency, it's got the orientation factor, and it's also got that activation energy in there. And I'm going to spend a lot of time talking about this equation, and I'm going to try to illustrate some of the math of it and try to do it in a kind of a simple way so that hopefully you'll be able to understand it. And some of you will actually like it, I think, I hope. But anyway, it's called the Arrhenius, even the name is hard to pronounce, equation, because this guy was Swiss, I think, so. And K is, okay, so this is the rate constant. This is an equation for rate constant. And it's going to explain why it varies so much from experiment to experiment. So it's equal to A e to the minus EA over RT. Now this E, that's the inverse function of a natural log function, but I don't want you to get all crazy about it. If you don't have a lot of background and you don't really want to think about an E, what you should think about is that E is a number. It's just a number. It's like pi, you know, pi is, everyone knows it's 3.14 something something, and some people know it to 100 digits, but E is just a number. It's between 2 and 3. It's actually around 2.78. So not, it is kind of a magic thing, but it's really only a number. It's a small number like that. So, you know, I'll talk to you later about 3 to the minus x, and that's kind of what this function is like. But anyway, so it's got these different portions here, and this portion here, this first factor, we call this the pre-exponential factor. And guess what we call this? This is the pre-exponential factor. What do you think this is called? Seeing as this is an exponential here, this is called the exponential factor. Okay, well, that doesn't tell you very much of anything at all. But this pre-exponential factor is actually the product of two things that we've already talked about today. All right, it's actually equal to z, where z is the collision frequency. And like I said before, when you have, and that's multiplied by p, and p is what we call the orientation factor. So let me address these one at a time. Okay, the collision frequency, that is just what it sounds like. It's how often per second the molecules that need to collide, how often do they collide with each other? Okay, so this is really just the collisions per second. And this could be a huge number because there's a lot of molecules. You know, if you have a mole of some certain molecule in solution, like a 1 molar solution in a liter, that's Avogadro's number of molecules, 10 to the 23rd. So you can imagine you have, you know, 10 to the 22nd or 3rd of each of these A and B in the solution. And they're you know, these collisions per second can be phenomenally high. Anyway, okay. Like it's very common to see values that might be, you know, 10 to the 9th or something like that. So it could be a very huge number. So I think that's not so hard to understand. This orientation factor, okay, so remember some of the collisions are in the right orientation, but probably many more for certain reactions are in the wrong orientation. Like I showed you one reaction and I showed you one right way and I showed you 2 wrong ways, but there could have been 10 wrong ways. You know what I'm saying? So a lot of times there's more collisions that are in the wrong orientation than in the right orientation. And this orientation factor is the fraction of collisions that have the correct orientation. All right. So since it is a fraction, the fraction of collisions with the correct orientation, its maximum value for any reaction is 1, which would mean 100% collisions are successful. So this number P is basically less than or equal to 1. 1 is the maximum. Okay. So I'm just going to give you an example with some numbers. All right. So, and I would like to, I'm going to show you the role of this orientation factor. So let's suppose that there are 100,000, or rather modest collision frequencies. Let's suppose there are 100,000 collisions per second for a particular reaction. So that would mean that the Z would be 100,000 collisions in 1 second. Okay. And let's also suppose that 1 in 10 of them, so 1 in 10 collisions are in the correct orientation. And that would mean, so what would P be? What would the orientation factor be if 1 collision in 10 is the right orientation? Point 0.1, good. So 1 in 10, that's P, that's 0.1. And this is, okay, so that's 0.1. So now if I take this A, this pre-exponential factor, it's equal to ZP. So that's 100. I'm just going to use some dimensional analysis here. 100,000 collisions per second times 1 correct orientation for every 10 collisions. Okay, that's the 1/10 thing. Okay. So you could see I can cross out collisions here. And this means I have 100,000 divided by 10. That's 10,000 collisions of the correct orientation per second. Because what I'm left with here is this divided by that. These units have canceled. So you could see that that dropped down the collision frequency by a factor of 10, because 1/10 of every collision are the ones that are the correct orientation, and the other ones we just, won't even talk about because they're not in the right orientation. So you could see that. So what if 1 in 50 collisions was correctly oriented? Well, 1 in 50 is 0.02. So instead of this being 0.1 here, like this is actually 0.1, if it wasn't 0.1, if it was 0.02, well, that's going to mean even fewer collisions are in the right orientation. Okay, so that would mean only 2% are the correct orientation. Here, we had, this was 0.1, or 10% are the correct orientation. So, you could see that some reactions might only have 1% that have the correct orientation. So there's a lot of variability there. And so this P factor can reduce A a lot. Okay, you might have a giant collision frequency, but if you have a specific orientation that's required, it would bring that number down by quite a lot. So this P is always a fraction. It's always less than or equal to 1. 1 is the maximum. So I'd like to sort of ask the question, when could it possibly happen that all collisions would be of the right orientation? When would there be no incorrect collisions? So what type of scenario would have all collisions be the correct orientation? So when would that P equal 1? 2P, what do you mean? Somebody said it, almost Chelsea. What do you mean? She said 2 pure elements reacting, but what does a pure element consist of? Pure elements consist of what type of particle? Are they molecules? What do pure elements contain? They contain atoms, and that is absolutely the right answer. Okay, so if you have 2 atoms, like let's say hydrogen plus another hydrogen, forming H2. I'm a terrible artist, but you know, it should be more symmetrical than that. There, all right. So you've got hydrogen and hydrogen forming H2. Does it matter how these two approach each other? Is there, you know, if you rotate this atom around and you have the other side meet this atom over here, it's all the same, right? Because what the thing is that atoms are spherically symmetrical. And it doesn't matter how two single atoms approach each other. All of those approaches are going to be the right orientation. Two atoms, single atoms, will always approach each other in the correct orientation. But that's not the case for molecules, right? Because you might need to have two atoms approach each other, like we had with the Cl and the N. But if the O goes to the Cl, right, because you got different atoms in a molecule. And so only when you have two single atoms approaching can there be a P equal 1, right? That would be P equals 1. If there are any incorrect ways the two particles can approach each other, then this P, this fraction of collisions with the correct orientation, will be less than 1. Okay, so in most cases, it's going to be less than 1. Okay, so that is the first part of the Arrhenius equation. K equals A, e to the minus EA over RT. This A is P times Z, whereas I told you this was the collision frequency, and this is the orientation factor. Okay, and we've checked off this, we've done. Talked about that. All right, now I got to talk about this part. All right, so this is the exponential factor. This is really a very important factor. It's really quite a big deal, and it has to do with that activation energy, which you see the EA here is what we call the activation energy. So I've got to tell you about the energy profile, you know, what happens to the energy over the course of a reaction happening. Okay, so I already said that if you had two molecules, A and B, they form this collision complex. Okay, so let's say we've gotten to this point. So let's say A and B collided. And let's say they even collided with the correct orientation. Then what we have here is called a collision complex. It hasn't reacted yet. And in fact, quite a few collision complexes fall apart without reacting. So collision complexes can and do fall apart without successful reaction. Okay. So let me show you what we call the energy profile of a reaction. You know, when we get to certain units, like the unit on solubility, the unit about even pure compounds, the hardest thing, I think, was the part when we got to, you know, the role of energy, because there's energy involved in so many different things. You know, we talked about energy that's required to pull apart intermolecular forces, energy released when you put them together. Now we're talking about the energy profile of a chemical reaction. So energy is on the y-axis here, okay? Things that are lower down on the energy scale are more stable. Things that are higher up on the energy scale are less stable. So let's say we start out with reactants over here. I'm just going to call that R for reactants. And let's say we're talking about, just for the moment, an exothermic reaction. If it's an exothermic reaction, will I draw my products up here or down here? What does exothermic mean? Is energy absorbed or released?
Released.
That's right. Energy is released. If energy is released, then the system ends up at a lower energy than where it started. Actually, I'm going to shift this over a little bit. I need a little more room here. Okay, so this will be the products. And it turns out that the path of energy that these reactants have to go through is they have to go up before they could go down. And this bump here, this energy here, is what we call the activation energy of the reaction. So, you might ask, why can't the system just start here and go down here? Why can't the reactants take this route? Why does it have to go over this bump? Why is there a bump? And the answer is that bonds have to get disturbed, and even broken before new ones can form. And so you end up going to a higher energy place, a less stable situation because of all the distortions of different bonds and things like that. Bonds are lowest in energy when they're a certain length, which we call the bond length. If you stretch that length, or even if you shrink that length, it's actually going to be less stable than the normal length where bonds usually are. So basically, the energy bump is there because in order to react, bonds are stretched or even shrunk. Okay, they are distorted. And this means they have a higher energy. They are less stable. And that's why you end up having to go here, and you can't take that direct route like that. And I don't want to tell you that every reaction is exothermic. We know that's not true. There are reactions that are endothermic where you end up here. So here again, we would have an energy profile would look maybe like that. Okay, and again, you have an activation energy. That's the height of this bump. Between there and where you started is the EA. Okay, now the other parameter on this curve, these curves here, is going from here down to here. That's the delta H of the reaction. Okay, and this delta is negative because it's exothermic. The products have a lower energy. This delta H is positive, okay, because it's an endothermic reaction. Does anyone have a question? All right. So this high energy place where we have all this distortion in the lengths of bonds and things like that, We call this the transition state. And we give it a symbol. It looks like a funny, like almost a railway symbol or something. So this is the transition state here. That's at the top of the activation energy bump. Okay, we call it the transition state. So I'm going to go back to that other reaction that I was talking with you about earlier, and show you which bonds get stretched and how that all works out. So here's that same reaction. These are a little bit light. It's not too bad. ClOON. And then we have NO. All right. So what happens in this reaction, which I try to illustrate in this picture actually represents the transition state. So what happens is that these two bonds here, oops, I wanted that to be red. This bond and this bond, the red bonds stretch. And that requires energy. And a bond is going to form between this N and this Cl. But you can see I've drawn here, these are the bonds that get stretched. In fact, I kind of.
We're just outside. No.
Ashley, are you talking to me?
No, I was talking to my dog. I'm so sorry.
Oh, that's okay. All right. Okay. All right. So these two get stretched, and this one has not formed yet. Not really formed yet. So when bonds form, that reduces the energy, but that hasn't happened yet. So you end up with a state that's actually higher in energy than where you started and where you end up. Okay, so it says the NCl bond of NO2Cl must stretch. That's this one. The NO bond here must stretch, and the transition state forms where the Cl atom is shared by both reactant molecules. Okay, and we call this the transition state. Sometimes it's called the activated complex. Lots of different terms for it. You know, in biology, you would have the enzyme substrate complex at the top of the activation barrier. I don't know, what do they call it? The activated complex, probably. So anyway, finally, you come down to products, and this is at a lower energy. Okay, and in fact, let's see. I think that this is an endothermic reaction. Yeah. I think I actually show you what the energy diagram looks like for this a little bit later. Yes, it is exothermic. Okay. So it's kind of like that for this reaction. Energy going this way. All right. So the thing is that the activation energy is also hugely variable. And that means that that exponential factor can vary a lot as well. Okay, let me just, hold on. All right, good. So you can have a situation maybe where, you know, here you have a tiny little activation energy, maybe 5 kilojoules per mole, or you can have 10 times that. It could be 50 kilojoules per mole. And let me not leave endothermic out of this. You can have a situation where that's 100 kilojoules per mole. So you could see you have, you know, quite a difference, 5, 50, and 100. And believe me, there's more variation than that. Okay, so the question is, you know, how does this affect the rate of the reaction? Is the rate constant really affected by that? How much is it affected? So how much is the rate constant affected by changes in the activation energy, EA. Okay, so what I'm going to do is just a little, I want to tell you that because this Arrhenius relation, it has this EA in the exponent. When a number is in an exponent, it really has a huge influence on the value of that function. So I'm going to do this is a really kind of silly illustration to show this to you. So suppose what I'm going to do is I'm going to contrast two different mathematical functions. Suppose we have f of x is 3 times x. And then we have f of x is 3 to the minus x, right? Remember that e is very close to the number 3. So it's like I'm sort of doing an illustration of 3 times e versus e to the minus x. Let me just put some numbers in, okay? So suppose x is equal to 6. So 3x, so this is f of x. F of x, no, sorry. So we have f of x equals 3x, which I just wrote. If x is equal to 6, then f of x equals 18. All right. If we double x, so I'm going to change x, I'm going to double it. So now I'm going to go to x equals 12. So what is f of 12? Oh, gosh, I didn't mean to put this here. I wanted to put 3x on top. So still f of x is 3x. Sorry, I messed that up. Now x is 12. So in other words, going from 6 to 12 with an ordinary function like, oh, let's multiply that x by 3. Now I'm multiplying x by 3. So now f of x is 3 times 12 is 36. So x doubled. And f of x also doubled. It went from 18 to 36 when x went from 6 to 12. Well, I want to compare that to if the function is 3 to the minus x. So if x is equal to 6, what is 3 to the minus 6? That's, if you remember your math, you know, when you have a negative power, this is really 1 over 3 to the 6, which is 1 over 18. No, it's not. 3 to 6 is not 18. Oh, God. I'm steering you all wrong. Sorry. 3 to the 6. Oh, that's not right either. Is 729. So this actually comes out to 0.0014. Okay. Now, if we double x, so x is 12. And now we calculate 3 to the negative 12. That's 1 over 3 to the 12th. And that 3 to the 12th is that's 531,441. Look at that number. Okay. And if you take that and figure out what it is, it's 1.88, let's call it 1.9 times 10 to the negative 6th, or 0.0000001, 2, 3, 4, 5. So look at that. So what I want to show you here is when we had like an ordinary function, just multiply 3 by x. We doubled x, we simply double the number. Now, this number is different by 10 to the 3rd. So we changed the x value and calculated it again. We doubled, this went from 6 to 12, and that changed by a factor of 1,000. So I guess my point is, my point is that when a number is in the exponent of a function, it has a huge influence on the value of that function. That's why I did this whole stupid example, okay? When a number is in the exponent of a function, changing it has a huge impact on the value of the function. So, you know, when you see something in an exponent and you're talking about variations in it, you have to pay attention because those variations can be huge. All right, so maybe I screwed my example up a little bit. I hope not. But I hope that you at least got the idea that this exponential factor is really very important. So relatively small variations in EA have a real impact on this e to the minus EA over RT. Okay, so enough with the math and telling you that. Actually, I have another example coming up, so it's not really enough. But I want to tell you what is the physical interpretation of this e to the minus EA over RT. And what that actually is physically, if you think about it, well, I don't expect you to have thought of this, but it's actually the fraction of collisions that have the activation energy, that have the required energy to go over the barrier. The fraction of collisions that have the needed energy to go over the barrier. So this fraction varies a lot, like I said. So let's talk about some examples. This fraction, what is the maximum value of any fraction? It's 1, right? That's, you know, the whole, okay? This fraction can be close to 1. When will it be close to 1? It'll be close to 1 if that activation energy is a small number, because there's a certain amount of energy that's available to all molecules that are moving around in a solution. We call that thermal energy. That's energy due to the fact that the temperature isn't 0. There's motion energy of molecules. This fraction can be close to 1 if the activation energy is low enough that the sort of natural thermal energy is enough. Okay, so if the EA is low enough, you can even have a fraction. You can have this exponential factor being something like 1. Okay, well, let's consider, oh, and of course, if the EA is large, it can be very tiny. And values of 10 to the minus 9th are not atypical. So it really can be very tiny. So let me talk about this. This is e to the minus EA over RT. So what is this RT? Well, R is the gas constant, but you can't use it in just any units. This activation energy is generally given in kilojoules per mole, okay? So this R has to be in kilojoules per mole Kelvin. so that when you multiply it by, so R times T would have these units. Kilojoules per mole. Kelvin times Kelvin will give you kilojoules per mole. And you need to have the same units are needed for EA and for R. So that number is 8.314 times 10 to the minus 3 kilojoules per mole Kelvin. If we're talking about room temperature, it's 298 Kelvin. That's 25 degrees C. Okay, so if you multiply these two things together, it comes out to 2.48 kilojoules per mole. And that's actually a typical value of thermal energy that's available just at room temperature. It's not that much, but all right. So now what I'd like to do is do two different calculations. So let's find this e to the minus EA over RT, okay? This is the fraction of collisions with the needed activation energy. And let's do it for two different situations. Let's do it for, if EA is 1 kilojoule per mole. If EA is 1 kilojoule per mole, that's a very small activation energy. And if this is the thermal energy, right, because it's gotten from using the temperature. So you can see maybe if this is going to go up with temperature, like thermal energy goes up with temperature, like the kinetic energy of molecules goes up with temperature. That's what this is talking about. So if you take and figure out e to the minus EA over RT, let's first figure out EA over RT. So we already figured out that this RT was 2.48 kilojoules per mole. And if our activation energy for the reaction is just 1, that this comes out to 0.403. So e to the minus EA over RT is e to the minus 0.403. Now, how do you do that on your calculator? And what is this e to the thing? Some calculators will have a button that's an e to the x button, but what will you have to do on other calculators? Actually, it's like what we did yesterday. It's the inverse of the natural log. And on some calculators, it's second ln. So if you put in inverse ln of negative 0.403, or second, whatever it is on your calculator, or e to the x. Okay, I'd like to know what some people are getting for that number, just to make sure you're doing it right. So we're calculating e to the negative 0.403. Yes, somebody got 0.668. So if this is the fraction of, I didn't mean to cross it out. If this is the fraction of collisions with the needed activation energy, which in this case is just 1 kilojoule per mole, if this is the fraction, then we could say that 66.8%, right? Just move the decimal point by 2 places to make it a percent. That's the percent of collisions have the needed activation energy at room temperature at 298 Kelvin. But what if our and that's a pretty big fraction, but what if our activation energy is 50 kilojoules per mole? All right, now when we calculate EA over RT, like we did over here, it's 50 kilojoules per mole divided by the RT is still same temperature. It's still 2.48. So this number here is 20.2. So E to the minus EA over RT is E to the negative 20.2. And that number is 1.69 times 10 to the minus 9th. That is not a lot of collisions that have the required activation energy. That's a tiny fraction of collisions have the needed EA. Okay, which means if we move the decimal place here, percent. All right, so this is 1.69 times 10 to the negative 7% of collisions have the right energy. So if I was to ask you, which reaction is going to be faster? All other things being equal, which is going to be faster? So remember the rate constant okay, so in one case, this was 0.668. For the other case, it's 1.69 times 10 to the minus 9th. These have a huge influence on the value of the rate constant, right? And so, this will be way faster. This is going to be a lot slower because too many of those collision complexes just don't have that energy that's needed to go over that barrier. Okay, need some more space here. All right. So it's as if molecules collide and they try to get over that barrier, but they just don't have the energy to do it. So it's almost kind of like, maybe you're watching one of those competitive shows, where they have this humongous obstacle course or something like that, and they try to get over that hump and they can't. They comes back and try again and can't. Comes back. Finally, goes over the hump. Maybe I'm thinking of people running. They have those climbing walls or something, and you run fast enough, maybe you get to leap up high and you make it over the wall. But if you don't run fast enough, then you can't do that leap and you can't get over the wall. So you could have many these are unsuccessful attempts where they have to come back and finally success and going over the barrier. So it could take many approaches for this to happen. Many collision complexes just fall apart. You can imagine if you have the fraction of collisions with the right energy is this 10 to the minus 9th, that there's going to be a lot of things that are unsuccessful before you get one that's successful. Okay, so another thing I'd like to address is, why does a molecule, let's say, moving a little bit faster, why does that molecule have an advantage? Why will it go over the barrier more easily? So suppose you have a situation like this, where you have, say, an atom and a diatomic, and the reaction ends up giving you, say, this plus, so maybe like hydrogen plus Br2 gives you 8. Well, of course, that's the wrong size. I make this bigger. Hydrogen plus Cl2 gives you HCl plus Cl, something like that. Okay. So you can imagine that if this atom were just crashing totally, moving like crazy and hits this red one over here, that might result in reaction. Where if it was just, kind of moseying along and not really, not really with a lot of velocity or anything, that this might be unsuccessful. Okay, so motion energy, kinetic energy can be translated into reaction. You can use that energy to crash in and then maybe have the reaction happen. There's something else I'd like to tell you about. Let's suppose you had a situation where you have, say, 3 plus this, maybe something like this. Okay, and sometimes that kinetic energy could manifest itself as a bond vibration. Bonds vibrate, and if you have a big bond vibration here, and then this atom ends up going out here in that vibration, it's getting close to this one, maybe crashes into it, and then you would end up with, something like this, and then something like this. So a bond vibration or bond vibrational energy can lead to reaction. Here we had a motion energy, kinetic energy of an atom. Another thing I also could tell you is that even, and these are for when you have reactions just with one particle, you can have this guy forming just this plus this, where maybe a bond vibration here, a big bond vibration, an energetic, I guess I should say, vibration leads to this bond just breaking. And then you just have, you've got, basically you took A to B plus C. So there's lots of ways that energy in the particles that are actually reacting can lead to reaction. Now you have to remember that when you have a sample, not all of those molecules are moving with the same speed. There's a whole distribution of speeds, and it's the fast ones that will probably be the ones reacting the fastest. They've got more kinetic energy. It's not distributed equally in a sample. The speeds are all over the place in that Maxwell Boltzmann distribution. Okay, so anyway, this is the energy profile that I promised you before. This is for the Cl NO2 plus NO reaction. Okay, and it's an exothermic reaction. As you can see, the energy gets lower. And this is just a typical transition state diagram. So here is addressed in these last things, and I've talked about some of these. Where does the energy come from to get over that barrier? So it comes from the kinetic energy, the motion energy of the molecules, which varies, right, within a sample. You have some that are moving faster than others. You got a whole range of speeds, remember, from that Maxwell-Boltzmann distribution. And now I need to mention temperature, okay, because temperature is very important in determining how much energy there is to give out in a sample. The higher the temperature, the more energy there is. So at higher temperatures, you have more molecules that are moving faster. So what that does is it means that more of the approaches to this barrier here, more of these approaches will end up being successful because they will have the energy needed to go over the barrier. And so temperature is very important. Which is why we spend a whole lab doing the temperature dependence of reactions and the temperature dependence of the rate constant. So reactions are always going to be faster at higher temperatures. And so I do need to talk about that. And I'm going to start by giving you a few numbers. Okay, remember, we watched that crystal violet reaction. And we watched that color fade, right? It was CV plus hydroxide forms CVOH. Okay, and I'm going to tell you, look at this data. I'm going to give you some information. The temperature, when it's at room temperature, the rate constant, and this is, it's second order, so it's per molar per second, is 0.191, okay? At 35 degrees C, a mere 5 degrees higher, the temperature is 0.302, okay? It's increased by 60%. If we go up to 100 degrees C, this rate constant goes up to 22.9. You know, that's a really big thing. It's a really big thing. This is a 76-fold increase. If you write this as a percent, it's 7,600%, 7,600% increase in going from 25 to 100 degrees C. Now that seems like a really big change in temperature, but we don't use temperature in degrees C. Degrees C doesn't have an absolute zero. We use the temperature in the degree we call Kelvin, and we've used that in this class before. So 25 is 298 Kelvin. 35 is 308. 100 is 373. So this temperature, this increase in temperature here is only 3 or 4%, and yet it increases the rate constant by 60%, okay? And that's because the temperature is in the exponent. And when you change something that's in an exponent, it really is a big deal, okay? So why this increase in rate? So why does the rate constant increase so much with temperature? And and the reason is all the reasons I've been giving you. As the temperature goes up, what happens to the speed of molecules? Molecular speeds, we know that they increase in the gas phase. Well, they also increase in solution. Molecular speeds increase. And so molecules move faster. And more of them will have the required activation energy. And just to refresh your memory, this is what the Maxwell-Boltzmann distribution looks like as you increase the temperature. This is a higher temperature. And this is the number of molecules, or the probability, versus the speed. At the higher temperature, so the average speeds, which are kind of in the middle of this curve, average speed goes up a whole lot at the higher temperature. Okay, molecules are moving faster. More of them will have the required activation energy to go over that barrier. So how does this exactly work with that equation? And I would like you to bear with me for a little while because I have to talk about this equation. And it's not that trivial, but I think that, with certain, looking at it graphically might be easier to understand. So this curve, this is this crazy exponential, but let's just think about e to the negative x, right? We can think of this as x. So what does e to the minus x curve even look like? All right. So what about at x equals 0? What is e to the 0?
1.
1. Right. And as we go, okay, so as x, as x increases, let's see what happens. So at x equals 0, we have e to the 0, which is 1. That's the maximum value of this function. E to the minus x is 1 over e to the x. As x increases, e to the x increases. But 1 over e to the x, when you take 1 over 3, you get 1/3. That decreases, right? So this curve actually goes down like this, okay? We call it a decaying exponential. As x goes up, this curve goes down until when x is infinity, this thing is 0. If x is really large, e to the minus x is approximately 0. So it goes from 1 down to 0 pretty fast, okay? So now let's think of e to the minus ea over RT. We're going to plot that versus ea over RT. So it's really going to have the same shape as the e to the minus x curve, except instead of this being just a single number, it's a composite. It's the activation energy over RT. But let's think about it. What happened there? Because that's not sharing anymore. Okay, so we have the same shape here. Start 1, goes down. All right. So as EA, as the activation energy increases, EA over RT increases. So that means we're going in this direction on the curve. This is the direction for EA increases. So as the activation energy increases, the value of that curve, which means the fraction of collisions with the activation energy, that fraction will drop. As the activation energy increases, there are fewer molecules that have the needed energy. So as EA increases, follow the curve from left to right, and the fraction of collisions with the needed activation energy, which is this e to the minus EA over RT, drops. Okay. What happens as the temperature increases? Now, temperature is here in the denominator. Temperature is in the denominator of EA over RT. So as T increases, we go this way. EA over RT gets smaller. So we're going to follow the curve from right to left. This is as T increases. So as T increases, you've got more energy in that sample. You've got more thermal energy. And therefore, you're going to have more of those collisions that are going to have the needed activation energy to go over the barrier. So the fraction of collisions with the needed activation energy increases as T increases. Now, you know, it's nice to understand it both ways. It's nice to understand it in words. It makes sense. As the activation energy increases, fewer molecules will have that needed energy. That seems reasonable, okay? If fewer molecules have that energy, then that's a smaller fraction of successful collisions or collisions of the needed energy. And this exponential factor will be smaller and the reaction will be slower. Okay, so as EA increases, this drops and K is smaller. So the reaction is slower. Okay. That's great to understand in words. It's also great to understand in pictures. If you like to look at it from that point of view, you have a graph that I'm showing you here. As EA increases, you're moving that way on the graph and that fraction goes down. You don't really need to understand it both ways. As the temperature increases, well, temperature tells you how much energy that sample has. If it goes up, then the fraction of collisions with the needed activation energy, well, there's going to be more of them because there's more energy in the sample. As the temperature goes up, the fraction of collisions will increase. K will be larger, and the reaction will be faster at a higher temperature. Okay, so, if you like to understand it, that as T increases, T is in the denominator, so that EA over RT is decreasing, you're going this way, right to left on the graph. That's a good way they're all good ways to understand it. I just want you to be able to explain it to me, okay? I want you to be able to put it in your own words. And I think it's important for you to be able to do that. So I do want to get to another thing, which is to tell you about the lab, next week's lab. Well, I'm not so much going to tell you about next week's lab as to talk about, the equation that you end up using in that lab and the graph that you end up making. But what I'm going to tell you about the lab is that we're going to do some experiments like this week, right? Except we don't vary the concentrations. We do not vary the reactant concentrations. We already did that. We already found the rate law. That's not what we're going to vary. We're actually going to use, I don't know if it's the concentrations from experiment 5 or 6, or I think maybe it's 7. One of those, we're just going to keep the same concentration. We do not vary the reactant concentrations. We keep them constant. But we're going to vary the temperature. So Mrs. Sayak and I have all these temperature baths. I think actually we just used one temperature bath and we kept adding hot water, cold water to get different temperatures. We vary the temperature. And so we basically measure the rate. Remember, that's delta concentration over delta. Some of you haven't done this lab yet, but you'll do it tomorrow. Delta change in concentration with time. You measure this rate as a function of temperature, and you're going to get the rate constant at these different temperatures. So you'll have, like 15, 20 degrees C, 25, etc. And then we'll have the rate constant. And then we'll have to change and put this temperature in Kelvin at some point. And we're going to make a graph. And now I'm going to show you what you're going to graph and why. Okay, so we have this relationship that we've been talking about all afternoon, the Arrhenius equation. And so if I take the log, the natural log of both sides of this equation, this is still K, equals the log of A e to the minus EA over RT. So first I take the log of both sides. Then I use this rule of logs. And that's the natural log of AB is the natural log of A plus the natural log of B. And this is my A and this is my B. So the natural log of K equals the natural log of A plus the natural log of E to the minus EA over RT. Now, the only reason for doing this is to make our lives easier, not harder. And here's the thing, natural log and e to the x, these are inverse functions of each other. So when you take the inverse of the inverse function, you end up with the original with just this e to the, with just the e, this part. So the ln of e to the minus EA over RT is just minus EA over RT. So if you look at this and you just sort of mess with it a little bit, so I really didn't do anything. I took this t here, I wrote it as 1 over t. And I took this minus EA over R and I put it in parentheses and I put a plus sign, but it's really exactly the same thing. But when I think about it this way, I say to myself, oh, if I'm varying the temperature, so this is the variable, so I'm varying T, and this has to be in kelvins. If I vary T and this K, this is the K, the rate constant at temperature T. Okay. And so if I go back to my data in this column, the next column, I'll put log of K and I'll take the log of K. And now I'll put my temperature in Kelvin. Okay. And then I'll say, oh, what I really have to do, if I plot this log of K on the y-axis and the 1 over T on the x-axis, EA over R is a constant. It's the slope minus EA over R. This is a constant for a given reaction. So what I've got here is Y equals mx plus B plus mx. So if you do a graph of the natural log of K versus 1 over the temperature in kelvins, okay, it'll look like this. And you'll have your various points, however good they are, I don't know. But the slope of this line, and this will be the log of K as a function of temperature, the slope is negative of the activation energy over R. And R is known. So that means that minus R times the slope of that graph is the activation energy. And so we will find the activation energy for the reaction. We will also find the y-intercept, which is equal to that frequency factor, that A, that pre-exponential factor. So the y-intercept, oh, I'm sorry, it's not A, it's the log of A. So that means if I take e to the y-intercept, it's going to be the frequency factor. So you can get A and EA from this plot. And that is what you're going to be doing in lab next week. Okay. All right. It's 3:30. I have a very nice set of exercises for you to work on. It starts with just going over this is directly from the notes. You may just copying a few things to sort of reinforce the ideas. It shows you what one reaction, this is the transition state here. That's this thing, the high energy state. And it asks you what you think the P value would be, very generally. It has a couple of reaction profiles here, and it tells you what the EA is and what the delta H is, and asks you, well, what's the EA? What would it be for the reverse reaction? This would be EA for the reverse reaction. This would be the EA for the reverse reaction. So we didn't do too much on that, and it's a good idea for you to do that. This tells you what the activation energy is and what the delta H is, and asks you, well, it asks you to draw the profile and then find out what the activation energy is for the reverse reaction. And this gives you an activation energy and a temperature, and asks you for the fraction of collisions that would have the required activation energy. And you probably should use 8.314 times 10 to the negative 3 kilojoules per mole. And then there's one more question. Ooh, I guess I forgot to put it in. There's a couple more there. So I'd like you to work on that handout. If you want to go into a breakout room because you got some people you want to work with, I'll open up some of those. And I think that's all I got to say. So what are all your questions? Because you probably should have some. Happy to answer them. Yeah, the recording. I actually am going to stop recording now because it doesn't make sense to record for this last part. But yeah, sometime this evening. Yeah, that's okay. I know it was dense. I know that. There's a lot of information here. Yeah, sorry. It's just one of those classes, you know. Yeah. I love it too. It's really my favorite, one of my favorite things. Especially that the whole fraction of, molecules with the appropriate energy and all that's really very interesting stuff. Thanks. Yeah, I'll put that Zoom recording up as soon as I can. I got to get the one up for lab yesterday too, and the notes. I'll do it. I'll do it. Those of you who are leaving, make sure you budget some time to study this stuff. It's important.
Professor, are you going to go over like the answers to this next class, or is this just for us to do?
Well, I would go over some answers with you today, but I'll post the solutions. That's what I will do.
Oh, okay.
Take last time to go over it, unless you want to do it. I mean, I have enough, really, I'm going to say there's still time, but yeah, 15 minutes is not enough to do it all anyway. But I mean, if you have a question next time about a particular question here, I would rather address it that way than go over all of them. I don't have time to go over all of them.
Yeah.
Okay. I will post the solutions and I will address any individual questions about individual, problems you have.
Okay, thank you.
Bye. Yeah, have a great day, everybody. Bye, Tyler. Oh.